Outdoor 2.4 GHz band Wi-Fi networks performance characterization. Abstract. The task of proper network planning with little or no attenuation has been the major target of communication engineers. To achieve this target, network planners, communications infrastructure vendors and the academia, all over the world have been studying the propagation characteristics of signals to enable them establish networks that suit specific terrain characteristics, such as differences in weather conditions, building structures, trees, and other vegetation, which may cause attenuation and/or obstruct the propagated signals from getting to its destination, thereby offering better coverage and quality of service, QoS. To understand these parameters within the Akwa Ibom State University, AKSU, environment, empirical measurements were taken and from the analysis, the path loss exponent for outdoor environments in the 2.4 GHz band found to be 1.999. In comparison of the graphical plots of different models, the measured model and cost 231 Walfisch-Ikegami model were adopted for network planning in the terrain. 1. Introduction. Wireless signal characteristic changes as it travels from the transmitter to the receiver. These changes depend predominantly upon the distance between the two antennas, the path, S, taken by the signal, and the environment, vegetation, rivers, and buildings, that makes up the path. It is therefore possible to profile the received signal from the profile of the transmitted signal taking into consideration the properties of the medium between the two. These properties of the medium are bundled into what is generally known as channel model. Channel models describe how the channel functions such as path loss, shadowing and multipath affect the properties of received signal that has traveled through the path. This is to say that the performance of any wireless link is a direct function of the terrain it is deployed. As such, careful network planning has become increasingly critical with the rising deployment, coverage, and congestion issues associated with today's wireless local area networks, WLAN. The determination of the path properties as well as the proper application of such path properties in the design of wireless networks is therefore very essential. This way a network planner can determine the placement and infrastructure required to meet the demands of the network for a deployment of any size, guaranteeing good quality of service, QoS. The issue of networking arose when there was need to transmit data from one system to another, most especially in multiple system environments. Networking was introduced either as local area network, LAN, wide area network, WAN, or made to cover the metropolitan, MAN, WAN. Area networks, AN, could be wired, wireless or hybrid of both access technologies. Wired ANS involve the use of cables to link one communicating device to another. Cable-enabled LAN is almost impossible in some buildings and expensive due to the high cost of cable requirement. Wireless communication, on the other hand, comes with huge flexibility and mobility, eliminating cable length limitation, difficulties experienced in laying and maintaining structural cabling methods as issues like rodents, cable cuts, and damages are very common, and most African infrastructures were not designed with network cabling in mind. Other benefits include the dynamic network formation, easy deployment, and low cost in some cases, making wireless technologies an appealing networking technique for broadband services in Africa too, the demand of which has maintained consistent growth. The most popular technology used for wireless local area networks is the IEEE 802.11b/G3. 802.11 compliant networks are based on direct sequence spread spectrum, DSSS, transmission technique or orthogonal frequency division multiplexing, OFDM, 4. Using 13 frequency channels with 22 MHz bandwidth and 5 MHz spacing, 802.11 technology occupies a total bandwidth of 82 MHz from 2410 MHz to 2483 MHz, taking advantage of CCK-OFDM modulation. 802.11 WLANs are capable to achieve a bit rate of 54 Mbps, 802.11 grams, 5. With the proliferation of wireless local area networks, WLANs, and impending congestion that follows, careful network planning and propagation modeling have become essential to help planners determine accurate path loss profiling and coverage plan for the networks. The drive therefore is to study the path loss characteristics of Wi-Fi signals in rural/suburban Africa terrain. 1.1 Review of outdoor signal propagation. In reality, the amount of power transmitted from the transmitter usually reduces as it passes through a medium, hence, the signal strength is said to be degrading with distance. Path loss is the difference in dB between the transmitted power and the received power, and represents signal level attenuation caused by free space propagation, reflection, diffraction, and scattering as a result of obstacles on the path of the signal. Figure 1.1 illustrates path loss in a typical wireless communication system. 6. Proper network coverage planning requires a good understanding of the fundamental limitations caused by diverse radio signal propagation mechanisms due to variable environmental conditions. According to 7, these phenomena induces signal scattering, fading and shadowing along the signal path, and their effects can best be described, in a large scale, by the path loss exponent, which defines the rate of change of attenuation that the signal suffers as it propagates from the transmitter to the receiver. The average path loss for a transmitter to receiver separation is expressed as a function of distance 8. Employed using the Okumura's model to determine the propagation range of IEEE 802.11 radio lengths for outdoor applications. Similarly, to evaluate the performance of 802.11b, 10 used 2 laptops equipped with Orinoco WLAN cards, and 2 PCs with D-Link WLAN cards. 11 to 12 also used empirical methods to show the coverage area and the signal strength inside the coverage area to reveal the technology that gives better WLAN. 13 using computer simulation of a typical 802.11b/e access to an IP core network through an access point in an infrastructure WLAN. 14 to 16 carried out measurements of transmission on microwaves bands were taken at 12 different locations in the University of Essex campus using laptop, USB adapter, access points, and GPS. At each location, 25 signal strength sampling from the access points, APS, were recorded. Simulations of the measured values were carried out using the Excel, XML program, Haver sign formula, and Fry's propagation law. It was noted that each of the access points degraded in throughput by certain percentage due to interference from other neighboring access points. Our interest here is on the path loss exponent on February 4 GHz Wi-Fi. 2. Research methodology. The research work was carried out in Akwa Ibom State University, AKSU, main campus located at Ikot-Okpatan, Gaypatanan local government area in Akwa Ibom State. Akwa Ibom is one of the states in south-south region of Nigeria and shares boundaries with the Atlantic Ocean, Cross River State, Abia State, and River State. Akwa Ibom State University, AKSU, terrain is swampy in nature and consists of several vegetation and foliage, which may cause obstructions to signal propagation. For the purpose of this project, the AKSU main campus was classified as a suburban community which consisted of students and staff, buildings, offices, and lecture halls, as well as sparsely located story buildings and trees, although located in the rural suburb of the state. 2.1 Test bed setup. The test bed consisted of a Wi-Fi radio, GPS receiver, a laptop, pen, and recording book. The received signal strength, RSS, on Wi-Fi interface were detected by the Insider software running in the laptop, and the measured signal strength recorded as shown below in random position of equal distance increased at interval of 10 m from the transmitter location. The 2.4 GHz access point was set up at a fixed position in a 5 m height in the university environment, and through the use of GPS the exact distance of the mobile device was measured and recorded at intervals of 10 m until 100 m. At each distance, 20 signal strength measurements were carried out, and the same measurement was repeated for different distances ranging from 10 m to 100 m. The mobile device maintained at an approximate height of 1.5 meters. Using the Net Monitor application of Insider software operated in the active mode and MAP76CSX GPS to determine the distance from access point, the received signal strength was measured at 2412 MHz and the average signal strengths were calculated. 2.2 Outdoor Empirical Propagation Models. To ensure that proper network planning is carried out in a particular terrain, it is necessary to employ a suitable propagation model that best fits such terrain. Rampantly, installers adopt ad hoc mode of outdoor Wi-Fi coverage where they place radio infrastructure in small test areas and through measurement surveys verify coverage, and then repetitively more and more areas are added until full coverage is achieved. This is in no way a professional method of network design. It is necessary to adopt an adaptive deployment design methodology, known as infrastructure mode. In this mode, a predictive deployment and network calculations are done using an accurate path loss model. There are several models which can be used for predictions in the outdoor environment. Such models are grouped into 3 major types: empirical models, semi-deterministic models, and deterministic models. We will briefly discuss some empirical models here. 2.2.1 Free Space Path Loss Model. The free space path loss considers the reduction in signal strength even when propagated in a vacuum without obstacles. This sounds ideal, and the loss are accrued to spreading of the signal, the effective aperture of the receiver antenna, and the transmit power. The path loss is provided for isotropic antennas with provisions for others. 2.2.2 Okumura Hada Path Loss Model. Okumura Path Loss Model is an empirical-based model for irregular terrain. The Okumura-Hata model is the most popular model based on extensive measurements made in and around Tokyo in 1968, where Okumura's observations was formulated into a simple mathematical model of the form, plus, where a and b are functions of frequency, antenna heights, and path loss exponent, and d is the distance. Hata model employed the analytical approximation to Okumura model, and median path loss empirical model is widely used. The model is suitable for frequency range of 150 to 1500 MHz and a distance between 1 km and 20 km. Hata divided the prediction area into three set of terrain categories, namely open, suburban and urban area. The Hata model specifies the base station antenna height to be from 30 m and mobile station height from 3 m and room for correction factors. Addition 17. Okumura-Hata path loss model equations for different terrains are 2.2.4 Walfisch-Ikegami path loss model. Cost 231 Wi is a semi-empirical path loss model that takes the characteristics of the city structure under study into account. Such characteristics include heights of buildings, roof, widths of roads, W, building separation, B, and road orientation with respect to the direct radio path, F. The model increases accuracy of the propagation estimation, but it is more complex when compared with Okumura-Hata model. The model allows estimation from 20 m instead of 1 km for Okumura-Hata model, and mean path loss is suitable for the model. Cost 231 is restricted to the frequency, F, between 800 MHz and 2000 MHz, transmitter height, H, between 4 and 50 m, receiver height, H, between 1 and 3 m, and a transmitter receiver distance, D, between 0.02 and 5 km. Figure 2.6 illustrates the above stated parameters to be taken into considerations when conducting field measurement that is to be analyzed using cost 231 Wi model 19. The equations are 3 results presentation. Table 3.1 shows the mean received signal strength and the path loss calculated from 10 repeated samples for the corresponding distance at random directions from the transmitter in the outdoor environment. The path loss was calculated according to equation. From Table 3.1, the received signal strength, RSS, was plotted against distance to investigate the performance of the signals. The result is as shown in Figure 3.1 below. Figure 3.1, Graph of RSS against distance. 3.2 Determination of path loss exponent using linear regression. From Equation 3.4, the path loss exponent was calculated for outdoor environment within Akwa Ibom State University as equals 131.1365.5976 equals 1.999. 3.3 Determination of a shadow factor using standard deviation analysis. To compensate for shadow fading as the terrain is composed of buildings and other structures, the large-scale average path loss was predicted at 50 m as equals 60.09 plus 19.99, 10, 5010 equals 74.06, 3.5. Using the predicted path loss value, the squares of mean deviations were generated as shown in Table 3.2. Table 3.2, Relationship between measured and predicted path loss. Distance, where n is the number of measured data points, equals V351.240410 equals 5.93 dB. From standard normal curve, the shadow factor, xs must not be greater than 11.86 dB. Using cumulative density function and considering that the mean value is 0 dB and z equals 1.65, then 5.93 equals 1.65 equals 9.78. With this value, the path loss beyond reference distance is given by PL dB equals 60.09 plus 19.99 log dd0 plus 9.78, 3.7. 3.4 Application of existing models and comparison with measured result. Using the free space path loss, Okumura-Hata cost 231 Hata and cost 231 Wi model equations given in 2.2 and substituting HB equals 5m, m equals 1.5 m and f equals 2412 MHz, the model equations shown in Table 3.3 were obtained. Using the model equations in MATLAB, the required graphical plots shown in Figure 3.2 was plotted. 4.0 Conclusion. From Figure 3.2, the measured result was compared with existing propagation models. As depicted in the figure, it can be observed that the free space model is much lower than the measured result. Okumura-Hata and cost 231 Wi are much closer to the measured model, while cost 231 Hata model is higher than the measured model. Therefore, it would be better to consider cost 231 WI model for proper network planning in the terrain, as the error between the model and the measured result is lower compared to other models. The indoor path loss was characterized to PL, dB, equals 60.09 plus 19.99 log, dd0, plus 9.78 with an exponent of 1.999.